I'll try to start the second lecture. So yesterday I essentially just defined, open and like sigma 0 n sets or point class actually of a Polish space, and then the definition was kind of straightforward. And then, of course, the important thing is the following, right? I'll just write for a open sets, but let's say, okay, A, D, the complete separable metric space. Okay. Metric space, and then let's say U is just subset. And then let's say now it's sigma 01 definable if and only if U is open. Well, this is, more like a intuitive description, the statement. But that's, of course, all of you well known about this kind of phenomena. That's really basic. In the sense of reverse math, what I have to say is that if U is an open set in the sense of like our coding, then U is open, then of course, H is a member of U is sigma 01. That's we have mentioned yesterday. And so the point is the converse, right? So if phi H, this is actually, I use a kind of a small letter, but actually, it's for set variables. Set variable. So phi H is a sigma 01 formula. And something like so what I want to say is, so this direction means just this. And this direction means what? So phi H is a sigma 01 formula, and like if we have the situation that for any X, for any Y, for any XY, from A hat, if phi H holds and X is equal to Y in the sense of A hat, then phi of Y holds. Meaning that whether phi H is true or not, it's just based on the point in A hat. Then there's a U, open set, holds for open set, such that for any X in A, phi even only if X is a member of U, right? A holds. That's the meaning of the sigma 01 definable class of a Polish space is open. And the proof is still easy. Just the same as the usual proof in the distributed set theory. Just using. So the proof is. I don't want to describe, but by Green's normal form theorem, essentially. It's an easy exercise, and you can write down the statement with a Queen normal form, and then I can easily check this. And what is more important is actually this is effective. And typically in the sense that, so meaning moreover, so this is just, I mean, I didn't prove anything, but moreover, if well, phi x, let's say m, is a sigma 01 formula, and for any m, well, needed condition is for any m star holds, then is this a sequence of open code like this? I mean, yeah, m, sequence of codes for open set such that for any m and for any x, I mean, in A hat, so x is a member of UM if and only phi x m holds, right? So not only for a single sigma 01 definable set, but actually you can encode this uniformly, and we can take it like a sequence of open sets. And of course, we can do the same thing for a, I mean, similar thing statements are available for sigma 0n sets. I mean, we can do the same thing. Okay, so so for, but just n is standard. Let's see. Well, okay, I didn't mention, but this is provable within RCA0. That's of course the important part. I mean, RCA0. I mean, today, for a while, I just worked within RCA0. I mean, everything is just within RCA0. Okay. Now it's ready to talk about the continuous function. Oh, I mean, as I mentioned yesterday, and then many of you already agreed, but the definition of continuous function is kind of annoying when we work within RCA0. And I mean, when you read Simpson's textbook, probably. And then, so I want to clarify what's going on there. Right? I mean, so before talking about just, I mean, or for continuous function in second order arithmetic, just consider forget about RCA0 and just consider a general situation. So given a function from between some two complete separable metric spaces, and then so let's write S F BS, let's say, in it's just an F inverse of a BS, let's say. And then with this situation, what's happening is that the fx is equal to y. This statement is just saying that the fy is equal to this one, right? I mean, yes. That. ESF. Right. So Fi means that the maximal filter generated by a point Y. I mean, so that means, of course, Y is the unique point of B of Bs such that the X is a member of the F inverse of. This is just the trivial rephrase the function. I mean, we only use the fact that the B hat is a T0 open set can distinguish the point. And then, but I mean, from this information, what's known is that, okay, I mean, for the functions on Poiss space, to define a function, we only need this information, right? I mean, all the pre-image of the member of base. And so to define and if it's continuous, of course, I mean, this is an open set, so this has to be an open set, right? So what we need to encode continuous function is just the encode all of these things, right? I mean, okay, so I'll try to say a code for an continuous function f from A hat to B hat is just it's a sequence of sequence phi, such phi, I mean, the form phi is something like a, well, let's say phi f, something like a bs. This is a base on the B hat. This kind of thing. But what's that? Needed condition is, so this has to be this is an open set for a open set. Each of them is a code for an open set. And well, together with the extra assumption, let's say, I mean, to make that, so this should form a family of all pre-image of this kind of thing. Well, we may add extra condition to make the code more efficient. So that's what that is. So for any A, that's that. For any A, for any point x, well, okay, it's right f of fx. So this is just a new notation, but defined by, I mean, bs in B, we have it's a member of phi f bs. So here's actually, so this is so these are all open set. So this is actually sigma 01, right? So this is actually a CE set, CE subset of, I mean CE or sigma 01 subset of a based on B. So this is, so for any x, well, let's say at least this forms a filter. This forms a filter means that, okay, so this sequence of open sets, well, it's, how to say, doesn't have any conflict to define a function, more or less. It's consistent or compatible, I mean, each other. And then, okay, now. And well, the definition continues, but so X is a domain of F, or I don't know, maybe we should write X is a domain of VF, probably. Just means that this Fx forms a maximal filter. So sorry, I mean, I said this is a code for continuous function, but actually, precisely, well, this is a possibly partial continuous function. But I mean, so the domain is defined in this way, right? And so why I only add the condition that this forms a filter? Because I mean, so this forms a filter is just the pi1 statement. This can be described as a pi1 way. While it's being maximal, it's pi2. I mean, it's more complicated. So I just distinguished the situation. I mean, so well, just to make sure. So this is, I mean, this of course means that the for any m exists Bs about B base B such that Bs is well 1. So f of fx. And this is actually, this is a rephrase of the x is a member of phi fbs, right? So this is sigma 1. So the whole thing is pi2, right? And of course, I mean, I should mention that the observation, of course, you can easily check that if you let it with like Simpson's textbook. I mean, otherwise you forget about it. But this definition, it's just equivalent to the definition to the in Simpson's book. If you know it, I mean, you can easily convert the code each other. I mean, one can easily calculate. I mean, over RC0, over RC0. Well, RC0 is not really essentially needed, but I mean, over good enough. Which theory, one can easily convert the codes in the Simpson's textbook if you know it, and this version. I mean, it's just the same statement. And I've already mentioned several times, but what important is that so this is just a remark. But the important observation is that, of course, if X is a member of domain of F, then Fx is equal to Y. It's this means what? So this means, I mean, the filter fx is equal to the filter generated by Y. This is, of course, the is a definition. It's either 1, of course. And if like and also if phi z is a like phi 1 or sigma 1, then you can easily rewrite a statement something like phi of fx is also either 1 slash sigma 01. So actually this is effectively delta 01 defined object. So if you want to write this in a kind of official way, of course this means that phi of, so this is officially, there is y in B hat such that phi of y holds and y is equal to f of x. So that's the official way of writing this statement in second order arithmetic. But of course, it's equivalent to a pi 1 or sigma 01 formula. If the original one is pi 1, then it's equivalent to pi 1. And the original is sigma 1, then it's equivalent to sigma 1. So, I mean, for continuous function, we can usually, freely use this type of, this way of writing. That's acceptable. That doesn't make the, the complexity of formula. So we can freely use this way of description. And of course, another important thing is trivially, fx is a member of some ball or open set. It's sigma 01. I just emphasized this, but trivial from the definition, of course. Right, so this is just x is a member of phi f bs. It's trivially true. But then, okay, with the previous description of open sets, we merely face the previous theorem for describing open set for the continuous function. So, the idea is something like this. If you want to encode a function f, and fx is a member of, will be a member of some open ball in B hat, well, f is imaginally, it's a function, continuous function from A hat to B hat. And then if this is sigma 1 definable uniformly for Bs in all bases in B hat, then of course we always have then there exists a code for continuous function EF after, well, satisfying this condition, right? Continuous code for continuous function, phi f, like for f, of course. It's rather hard to write down the idea. But, it's more like a intuitive idea, and the exact form is something like so this officially means just there is a sigma 01 formula, it's Bs is sigma 01, and well, if xy is in A hat and theta HBS holds and x is equal to y, then theta YBS holds. And the first condition, and the second condition should be more like if X is a member of A hat, then, well, let's say fx theta means that the collection of all Bs theta HBS holds. So this is a sigma 01 set. Forms a filter. Then there is, so this is the meaning of this. I mean, if H is a member of BS, is sigma 01, I mean, uniformly sigma 01 definable means precisely this situation. But I mean, you can easily capture what's going on with this situation. So I mean, so when you start working within like reverse mass for analysis in a setting over RC0, maybe you're afraid of like basic functions for analysis has a continuous code or not, for example, right? I mean, so like, but we can now easily see that, for example, from real to real, let's say like you want to define fh to be just polynomial, and xn a0 x0, let's say, no, I mean a0 polynomial. Is it continuous? I mean, you don't need to construct a code, but just what you have to check is that an xn plus so of course ai is all real number, and then of course so this is I mean so this is usually you may like I mean b minus s b plus s, right? I mean b is rational, s is positive rational. So consider this statement. Is sigma 01? Of course, yes, right? I mean, so there's a continuous function code in this, right? I mean, that's very straightforward. So you can easily encode like the fx of exponential maps. It's just the, well, I mean, I should, I mean, not analysis. I mean, I can easily make mistakes at this point. But so if you want to encode this, well, again, the same thing. Well, okay, so this power series is a member of some interval. It's sigma 1. Of course, I mean, if you know the speed of convergence for this, right? I mean, so it's large enough. And then the remain, I mean, part is just small than the approximation of this, then that's good enough. So this is sigma 1. There is a continuous function, and so on. So it's, I mean, and that's just, I mean, usual math. I mean, you never worry about a situation, I mean, coding or anything about special situation in RC0. Just the usual way works. Okay, and also, I mean, probably several, I'll try to erase the board. Oh, sorry, try to use this one. I mean,
That's actually the difficult part.
sorry?
That's actually the difficult part.
Okay. It seems it's still a lot of what we mean on the board. So I do. This is fine. Okay, the chalk is here. And so, okay, already forget have happened. So, okay, so like these basic functions can be easily encoded within RC0. And another thing that, well, you may first worry about might be something like so when you want to define a higher dimensional function on Euclidean space, then let's say consider this kind of situation. So F0 is in Rk to R, and F1 is also the same thing, and both continuous. I mean, given this continuous function, and then you often want to define a continuous function g from Rk to R square, or in general more, just by h to be f0x, f1x, like something like this. I mean, we are almost always using this kind of definition to define continuous function implicitly, but of course this is continuous because I mean both of f0 and f1 are continuous. Then of course the f0x, f1x is a member of some open ball on, like this is from R2, but this statement is still, this is sigma 1. That's all. I mean, this is a continuous function. You never need to check anymore. Or another probably useful thing is that and two easy corollaries. I mean, the first one is really trivial, but by the way, if I write in this way, is just say continuous means that the f is also total. Continuous. I mean, use it. Officially, I give a definition for partial continuous function, but mostly we're just interested in total continuous function. So let's always assume that, well, when we think about the continuous function on A hat, if I without mentioning anything special, we always assume that it's total. I mean, for any member of X, well, it's a domain of F. That pi2 statement is already true. So we would start with that situation. Okay, so now, I mean, what's needed? So the almost trivial corollary is that, of course, if U is an open set in B hat, then of course we get F inverse U is an open set. Well, more officially, I mean, and effectively. Meaning, but this is actually important, so I'll try to rewrite this in a more careful way. So what I meant is that so given a UN sequence of codes for open sets in B hat, then you may find then there exists a sequence of open codes in open in A hat such that for any n Vn is just the F inverse of Un. I mean, you can write down without using code even, but I don't want to do that. But I mean, you can easily check that. So I mean, almost by definition, you can always extract the inverse image of sequence of open sets effectively, directly. And another basic tool that we almost use all the time without mentioning is that, okay, so now if Fi is now a sequence of, let's see, open sets, sequence of continuous functions from some open subset of A hat to B hat, and they are continuous, then, and for any ij and for any x in the intersection of ui and uj, if fi x is equal to fi fj x, then there is a continuous function f from the union of all these things to be hat, right, as a continuous function. This is still true because, I mean, the statement that fx is in some open ball is still sigma 01. You can easily check it. There's some I, and fix is a member of the target open ball. So that's sigma 01 statement. That's easy, I mean, by definition. So, I mean, in many proofs, well, actually, you will define continuous function, I mean, in a piecewisely. I mean, just on this domain, I want to define continuous function. I mean, trivially, seems to be easy to be checked that it's continuous on this domain, that domain, this domain, and then take a union. That can be always justified. I mean, we can do that all the time. And also, I mean, okay. So what more important is that, okay, well, actually, we are lucky when we want to define continuous function, we're lucky the inverse image is open set, and we haven't code for open set, so we can define functions. But actually, I mean, we have a code for like sigma 0n sets, so we can do just the same thing for sigma 0n set, sigma 0n measurable functions, let's say. If the inverse image and open set can be coded in a uniform way, then you can always define a function that's of such class, right? I mean, so I would probably use a different color. I mean, so I just would try to rewrite the definition. So let's say sigma 0n measurable means that now this is now sigma 0n sets, right? And the main part is just the same. But the problem is now, okay, it forms a filter is now I 0n. And the thing we have to be careful is this part, actually. So now, okay, for sigma 0n measurable functions, what we have to take care is that, okay, now let's say x is a let's say pre-domain of f if this forms a maximal filter satisfying this condition. This is actually pi, well, n plus 1. But we still don't know if this is so in this case, this is in general, sigma n definable set. Right? I mean, so this is now not CE, now it's sigma n definable. Meaning that, okay, even if it forms a maximal filter, you don't know whether it is generated from a kind of a real point in B hat or not, right? So let's say we need a two stage for the definition. So the X is a domain of F, means that there is Y in B hat such that Fy is equal to F of Fx. But nonetheless, I mean, we usually don't need a value. I mean, very often, we don't need a value, right? I mean, when we do some analysis, actually what we need is that just the description of this kind, for example, or more like when you do, for example, measure theory, what you want is something is bigger than something or something is smaller than something, just relativized sense. And that means if we have a good description for I don't have enough space to write down, but maybe here. So if yes. So the important thing is here. Yes, I find the right part. So what we often need is just this situation. Fx is a member of some open set or not. I mean, member of a base or not. That's usually the needed condition. And this is, well, if X is a free domain of F, then this statement makes sense. I mean, in other words, X exists as a kind of an imaginary point, right? I mean, sigma 02 definable real. That's kind of a normal situation actually delta 2 definable real if n is sigma 2 measurable. So this is an imaginary point, and then so we can still state this kind of thing, and the complexity is just sigma 0n. Right? I mean, because I mean this is just this one, and this is a sigma 0n sets. So we already know the complexity, this statement. But the thing we have to be careful is that if X is a member of domain of F, then we want to rewrite, for example, some phi of G to be like phi of F. We want to use this kind of notation. But that's dangerous, right? I mean, because the complexity is very much different. So this notation is not great. I mean, when you think about the complexity of this formula, we really have to write in this way. If n is greater than 2, then okay, if you want to mention some point, and so the f of x has some special, I mean, more complicated statement, then we have to check in one by one. Now, unlike continuous function, that part is different. But other than that, we can actually deal with general sigma 0 n definable, sigma 0 n measurable functions within our C0 without changing many other ideas. And of course, this theorem is still true, right? I mean, if you can define the relation in a sigma 0 n way uniformly, then of course you can find then there exists a code for so now it's sigma 0 n measurable function code for f. That's also available, right? So I mean, the situation is just the same as usual math. I mean, in set theory. Nothing different. On the other hand, well, indeed, even with analysis, so you may feel, perhaps you may have a feeling that well, okay, with analysis, what we can do for analysis is just for continuous functions, but actually not, right? I mean, sigma m measurable functions is available, and actually, like, by sigma 02 measurable function, we can already define many more interesting functions. What? I forget where I put white chalk. Sorry, I will use a new one. But I mean, so with this way of coding, we have a kind of a uniform way to define various different types of functions. For example, like Bear class 1 function, I mean the pointwise limit of a limit of continuous functions. It's, of course, like meaning that hx is the limit of, if a function is described in this way, and if I is a sequence of continuous function, then of course h is sigma 02 measurable. I mean, sigma 2 measurable class of sigma 2 measurable function is bigger than Bear 1, but yeah, it covers. So we can always find a reasonable code for this in the previous sense. Or like if I would like to use this kind of term for, if h is a function from real to real, which is monotone, increasing or decreasing, then this is also sigma 2 measurable. I mean, well, precisely. So so what we want is that the H inverse of some open set is actually interval, right? I mean, so like just in a way like this for simplicity. But inverse image of open interval, if the original function is monotone, then it has to be, it's one of closed interval or half of interval or like one of them, right? It's all, of course, sigma 2. I mean actually just the Boolean combination of sigma 1 and pi 1. So we can easily encode these functions in a uniform way. So for example, we can always say something about, for any monotone function, we have something is a reasonable statement within our C0. Right? I mean, we can describe those things. Or yes, and another important thing is that I don't know, just an easy example, so I'll try to write here. But I mean, if from R to R is differentiable, if this is differentiable, then of course you can take the derivative. F prime. This is also, we can encode this derivative. I mean, if you know that it's differentiable at all points, then it's sigma 2. I mean, really, F prime x is I mean, not integrable probably, but we can still define function. And yeah, I think, well, so, okay, I have another example actually, sorry. And, well, maybe I will give a definition, I mean, later, but I will also use a lower semi-continuous function, lower or upper semi-continuous function in the next tomorrow, and that's also similar to measurable easily. So we can deal with all this kind of thing in a uniform way. That's what I wanted to say for today's talk. And okay, now I feel we are ready to do reverse math for analysis now. I mean, probably more like a bit more natural way within over RCA 0. Oh. Okay. So I only have 5 minutes more, so that I just want to like describe the known results of RCA 0 today, and then tomorrow I will give a proof for some of them. But so what's provable with RCA 0? I'll tell them. The following are provable within RCA 0, and the famous one is intermediate value theorem. The value LM, that's the statement for continuous function on real line, naturally described, and the mean value theorem. Mean value theorem. Well, now we have to mention the derivative, but that's fine, I mean. And like, there are many famous ones, like implicit function theorem, or inverse function theorem, on the Euclidean space, let's say. That's also available. And the usual proof works. I mean, okay, I mean, you may use derivative and so on, but that's all already available. I mean, just as usual. And well, I mean, and many more. For example, Taylor expansion is okay. Many more things, but for example, these things can be naturally described and then provable within RCA 0. Probably I'll have a kind of a quick proof for mean value theorem tomorrow, or maybe not. I'll calculate the time I can use. And then so over RCA 0, many things are equivalent to WK 0, as you know. And covering compactness for closed unit interval real, actually, I mean, that's almost the same as the definition of WK0 in the usual sense. And then, like, if a continuous function from the closed unit interval to R is continuous, then it's bounded. Or as a attains a max and minimum, it's uniformly continuous. Or if you know about the modulus of uniform continuity, having a modulus of uniform continuity, it's also equivalent to WK0. Or like a, for example, Cauchy's integral theorem or holomorphic function. For example, this kind of thing is also available, or Jordan curve theorem. One decent one, which I like, is Kihara's theorem, saying that the invariance of dimension meaning that there's no even for standard fixed n and m, there's no continuous one-to-one function from like R4 to R3. R4. No, I mean R5 to R4, R10 to R6. So those are all equivalent to WK0. And actually, R4 versus R3 is still open, I think. But if you generalize to the if you consider general level, that's just equivalent to WK0. I like that proof. So these are all equivalent to WK0. Of course, many more. And probably tomorrow I will show the short proof of the things for WK0. So I would mention that as well. And then talk for today. Over RC0, the Poincare equivalent. Weak Kenhi's it's equivalent to, for example, the most famous one probably is that, this has a measure 1 in the sense that, in the sense of although its external measure 1 is WKL0, and the one I've tried to show tomorrow is that let's consider continuous function on the closed unit interval, which is bounded. I mean, value is below 1 is nothing important, but it's Riemann integrable. Okay, from the definition of Riemann integral, if it's unbounded, then no chance. I mean, but I mean, on the other hand, okay, without WKL0, if a function is bounded, then actually it's integrable. Continuous function is integrable, and it's equivalent to WWT0. Or, I mean, the famous one is Vitalis covering lemma. I recently kind of restudy some basic part of functional analysis for real, like PD application, and then how the Vitalis covering lemma is used in the real context. But it's, yeah, I mean, approximation for like Lubech functions in Lubech space, for example, Vitalis lemma is essentially needed, but that's exactly equivalent to WWT0. It's important. And also,
Covering lemma?
sorry?
What is the lemma?
So I mean, given a covering for a, well, let's say the 1 unit interval, then you may take a more like a disjoint kind of a fake cover. I mean, you may fail covering some part, but still you can so that you can take a kind of a sub covering, which is disjoint but still preserving enough measure. That's the idea. But when you want to approximate some integral, okay, so you want to, well, decompose the domain to a like smaller ones but behaves better, and that's possible without losing too much information about measure. That's the idea of Vitalis covering lemma. And okay, I already my time already, but another one probably why I give a definition of monotone function is that any monotone function from, let's say, 1 to 1, it's differentiable at some point, or probably almost everywhere. That's almost everywhere. Actually, both statements. Almost everywhere means that the measure 1 points. This is also equivalent to WWT0. I mean, almost everywhere, then it sounds like a WWT0 statement. But actually, just differentiable at some point is already equivalent to WWT0. That's also known. And so these kind of things are available within RC0. Okay, I'll try to finish this part. Thank you very much. Sorry, 5 minutes longer.